Yeah, I mean, big thanks to the organizers and thanks to whoever canceled last week that let me have this talk because so yeah. So I'm going to talk about integrable systems. Many of the people here have seen me talk about integrable systems many times, I'm going to talk about maybe 3 or 4 different papers related to constructing integrable systems, and in particular, what I think of as sort of the like bifurcation theory of integrable systems. You're deforming the system in some way, you're seeing what changes, what stays the same. In particular, how can I start with a system that I understand a lot and deform it into a system that I understand not so much, and then kind of make this connection. And mostly, I don't know, I'll put a bunch of pictures on the board, some triangles and things. So we'll see. So I'll start with some stuff that everyone knows, and I'll transfer to some stuff that most people know, and then we'll do new things. So, right, if you start with the symplectic manifold, everyone in this room knows you can get the Hamiltonian vector field. There's a choice of sign, but it doesn't matter to me. And an integrable system, which is the setting I'm going to be in, a finite dimensional integrable system, is, right, I mean, the typical thing to say is that in mechanics, you think of this as a dynamical system or a Hamiltonian system with roughly the maximum number of conserved quantities. So you have some dynamical system where the total energy and the angular momenta and things like this are conserved quantities of the dynamics. The more conserved quantities, the more rigid the situation, the more you can understand it. And so an integrable system, we have a symplectic manifold M omega, and then we have a bunch of functions, F1 up to Fn, and I require that they Poisson commute. So, so these are supposed to be our conserved quantities, I guess. And of course, each of these functions has associated a Hamiltonian vector field, and you can take the flow of that Hamiltonian vector field, which is going to be some symmetry of the system. So this is like Noether's theorem, I guess. You have conserved quantities and you have symmetries. Right, so if I have an integrable system, I have a bunch of functions that Poisson commute. So Poisson, that's why I'm allowed to be at this conference. And I mean, it would be stupid if I said, you know, my system conserves energy and it also conserves energy times 2 and energy plus 4, you know. So these functions need to be independent somehow, right? So this is the setting of an integrable system. The functions aren't assumed to be independent everywhere. They're just assumed to be independent almost everywhere. And from my point of view, a lot of the interest is really concentrated on the singular points. And we'll see many pictures of sort of what's going on with this. But the points where the linear independence of the differentials fails are called singular points. And as I was just saying, each of the Hamiltonian vector fields of your integrals, that's these functions, generates an R action. And because they Poisson commute, the R actions commute. So we actually get an Rn action, right? I say a local Rn action because in principle, there's something to do with, you know, you need the manifold to be compact or the vector fields to be complete or something like this. Okay, so anyway, this is the setting that we're in. So I'll start with the nicest possible type of integrable system where everything works, and then I'll talk about trying to emulate this into more general situations. So a toric integrable system is an integrable system. So I have that part of the definition up already. Where furthermore, this Rn action is actually a Tn action. It's an effective action of a torus. So I'm thinking of this a little bit differently. I'm almost opposite direction of how people sometimes talk about it, right? People say start with a torus action and assume it has like a moment map. This isn't really any different, right? I'm starting with some functions. I'm saying assume that their flows give us a torus action. And then I'm going to assume that M is compact because it's easier to say things about toric systems this way. I mean, in fact, you can do quite a lot if M is not compact too. And we'll leave that. We'll remove that requirement at some point. So yeah, we can think of this as a Hamiltonian Tn action. And so the point is that if you look at the joint map, the moment map, which is all of these integrals put together, you have a map into Rn. And it's very well known, independently to Atiyah and Gilman-Sternberg, that the image of this is a polytope. In fact, it's the convex hull of the fixed points. So, okay, so let's try and push a little bit further. Moreover, not only is it that the image is a polytope, it's a special type of polytope called a Dalzon polytope, which is easy to define, would take 2 minutes, but I won't, I don't know. And even more than that, any such polytope can appear as an image. And even more than that, there's only one up to isomorphism toric system that goes to the polytope. So I've said this in kind of a weird way, but the easiest, I mean, essentially what I'm saying is this, is up to isomorphisms, there's a bijection between toric integrable systems and Dalzon polytopes. So if you want to know something about a symplectic manifold with a toric system on it, you can just draw triangles and squares and things, which is what I do. Anyway, there's more than this. So first of all, going from the toric system to the polytope is easy. It's the image of the map. You take the image, it gives you a polytope. Sort of surprisingly, maybe, going from the polytope up to the toric system is also pretty easy. There's like an algorithm that, I don't know, it takes 20 minutes. I forget every time I have to do it, but it's not so bad. You do symplectic reduction. And that's something I want to focus on. People don't often focus as much on this. The fact that it's a bijection, but one of the ways that he proves it's a bijection is by constructing in a really obvious way, a really accessible way, the inverse. And so this is something that I like, and I don't know, keep it in mind, I guess. So let's very quickly have an example that will be important for us later. I'm going to take S2 times S2. I'm taking the usual symplectic form on the first factor and twice the usual symplectic form on the second factor for sort of technical reasons. And I can take various functions. I don't know. These functions will be important in a minute. So the first J is, it's a function which is the height on the first sphere and twice the height on the second sphere. This is corresponding to the fact that I doubled its symplectic form. So the flow of J is going to rotate both spheres together. And the flow of H is going to rotate just the first sphere. So this is, you can think about it for a few seconds. You can see that these things commute with each other, and therefore it's a toric integrable system. And the image of these things is a polytope that looks like this. So this is the Dalzon polygon for S2 plus S2. Okay. So let's go further, right? I mean, now I should leave a little bit the things that every single person knows. In some sense, the next natural step is a semi-toric integrable system. So again, I'm requiring that it's a integrable system, but instead of both functions generating a circle, it's semi-toric. Maybe just one of the functions should generate a circle action. So I'll require that J generates a circle action. So we have a Hamiltonian S1 action that's given by one of my integrals. And then there's two slightly more technical requirements. One is I require J to be proper, which is automatic if M is compact anyway. And the other thing is this requirement on the singularities of the joint map, of the moment map. So explaining this in full detail takes a little bit of effort, but I can just say that in integrable systems, similar to in Morse theory, there's a concept of a non-degenerate singular point. And again, similar to Morse theory, there's like a local normal form for the non-degenerate points. So if you have a non-degenerate point, then locally it looks like one of this list of things. And so what I'm saying here is that the hyperbolic blocks are going to be blocks that I don't allow. That's like a type of singular point. It's like saying I have no index 1 points in my Morse function, something like that. I'll explain this a little better in 1 or 2 slides when I have pictures of the fibers that I do allow, which is maybe the easier way to think about it. I wanted to make a comment, which I already made out loud, which is that if you start with a semi-toric system and you just cover up the H, you have a Hamiltonian S1 space. And these are really well understood by Cartan's thesis, actually. Okay, so, right, so why do I care about semi-toric systems? I didn't want to just define something nice. But first, let's think a little bit about what they look like. So as I said, there's certain types of singular points, and in a semi-toric system, there's not that many possible points. So there's regular points. These are the points where all the differentials are independent. Rank 1 points will be points where DH and DJ are linearly dependent, and the only ones that can show up here are what are called elliptic regular points. And then there's two types of elliptical or of rank 0 points I can show. This is much easier to understand if I put the picture, actually. So, right, we have a map from our manifold onto its moment image. And the fibers of that map is what I want to think about. So if you take a regular point in a toric integrable system, and you take its, well, actually in any integrable system, and you take the fiber that it's in, it's going to be in a torus like this. This is like Arnold-Liouville, I guess. The elliptic regular points are the ones that correspond to the boundary in a toric system. These can also show up in semi-toric systems. These come with a circle. Elliptic singular points are just a point. I mean, this is like a corner on a toric system. But the thing that's interesting and new are these focus singular points. So I can have, some labels here. They're sort of like you're looking at a bunch of regular points, and as you get close to a focus point, one of the cycles of the torus is going to pinch. You have like this degeneration that happens, a sort of nodal singularity of some kind. And so you have fibers that look like this, which are extremely interesting for two reasons. One of the reasons is the fiber itself has interesting dynamics around it that you might want to understand. But the other reason is the existence of a single fiber that's pinched like this has a global impact on what the integrable system can look like. I mean, in a word, it introduces monodromy of the affine structure. So essentially, I've just added in one more type of singular point, but already things are going to get much more complicated. And I guess I can make a comment here, which people may be already thinking about, which is maybe you've heard of almost toric fibrations or almost toric systems, which is almost the same as semi-toric, right? This is going to be confusing no matter what, I guess. But the thing that so these are the same fibers that would show up in an almost toric system. The thing that I require that's different is the global S1 action, right? In an almost toric system, you always have local S1 actions, but maybe they don't like agree or they don't patch together in a nice way. And so this is what's a little bit different in a semi-toric system, and actually is going to be useful for what I want to do with them, even though you can do, certainly you can ask similar questions to the ones I'm going to ask about almost toric systems. Maybe, for instance, an almost toric system with only one nodal point is always automatically semi-toric. So there's many examples of semi-toric systems that people are interested in. Anyway, I will very, very briefly mention 5 invariants that I won't explain all of, but I'll explain at least one of them. But just the point is that there's 5 different things you can compute from a semi-toric system. And these 5 things completely classify the system. So the situation that we had in with toric systems is you look at the moment image, it's a polytope. That polytope determines the system up to isomorphism. In a semi-toric system, you have more subtle invariants. One of them, the second one, is the semi-toric polygon, kind of plays the role of the toric image, but it isn't actually the image of the map. It's a little bit more information than that, a little bit more subtle or difficult to deal with than that. And then there's other invariants that have to do with the dynamics around the focus point and things like this. I'll extremely quickly click through them as when I'm explaining them a little bit. But this result due to Plyo and Vunagak is that, well, is essentially this. Maybe it's easier to think of it this way. Simple semi-toric systems, so I didn't even say what simple means, I'll say in a minute, are in bijective correspondence to lists of these invariants. So there's essentially you can just start writing invariants and work entirely with the invariants if you want to, just like with the toric case, except now the invariants are more complicated, more difficult to deal with. So I can very briefly talk about this word simple. The point is that in an integrable system or in a semi-toric system, you have these focus points. And simple essentially means the focus points aren't interacting with each other. If they interact with each other, then the situation becomes more complicated. And you can have fibers that are like multi-pinch tori, like this one. And I can just spend one slide to say that we have also dealt with this case. So I have a paper with Plyo and Tang that if you deal with the invariants a little bit, you can still classify them in terms of a polygon, essentially, in the non-simple case. So I won't actually talk about the non-simple case, but it's not that much different. I guess that's what I want to say. Okay. So now that my talk is half done, I should say my goal, which is in relation to what I was saying about Delzon's theorem at the beginning. In toric integrable systems, you take the image that gives you the polytope, and from the polytope, there's this algorithm, you do some reduction, and that gives you the system. Globally gives you a representation of the system that you're interested in. The semi-toric systems are constructed in like a more abstract way, more like, oh, I know what it looks like around a focus point. There exists a function that can glue it to this. There's a lot of like, there exists a smooth function kind of arguments. And so it becomes really difficult to write down an explicit example of a semi-toric system. Say, oh, okay, I want to compute the invariance, or I want to learn something about the system. Let's write down a system is a really hard question, actually, which is a little bit, I don't know if it's surprising or not. In some sense, it's unavoidable because semi-toric systems are more complicated, and we're allowed to like do smooth perturbations and things change in a strange way. But at least when I was first thinking about this, I was thinking there should be some examples. There was essentially like one example known, which I'm going to show you. There should be an easier way to generate some examples that have some, if I draw some polygon, the abstract theory says there is a system with this polygon as its invariant. I should be able to write down maybe one system with that polygon, or if it's a really simple polygon, write down an example. And that's more or less the goal of the remainder of my talk. If I give you a polygon that I know is associated to a system because of it satisfies everything it's supposed to satisfy, can I actually write down a system that has that as its invariant? Okay, so in order to do this, I need to, talk at medium plus speed, I guess. I want to explain the invariance briefly. The most important invariant for me is the semi-toric polygon invariant. So if you start with a semi-toric system, the image is not a polygon. The image is just some random shape. It could be whatever. And you have along the boundaries, you have elliptic regular and elliptic singular points, kind of like the toric case. But more interesting things can happen in the interior. So I think, I'm going to draw some fibers. So regular points, the pre-image is a torus. The focus points can lie in the interior of the moment image. And they sort of mess everything up, actually. These are these pinched tori that live over the inside. And the point, I guess, is that when you have an integrable system, this torus vibration gives you an affine structure on the regular points. And in a toric integrable system, that affine structure is equal to the affine structure of Rn. And that's kind of why you can see the affine structure of a toric system. All of the data that you get from the polytope, you really are getting from the affine structure. It's just given to you as it's handed to you, all these angles and SL2Z lengths and things like this. But in a semi-toric system, you're not so lucky. And in fact, you can't like just straighten it out because the affine structure and the torus vibration has some monodromy around this point. So what that means is I can't just say, oh, I sent it into R2, but the affine structure is wrong. Let's just like compose with some diffeomorphism to straighten out the affine structure. The monodromy inhibits that. But there's sort of a simple idea to fix this, which is due both to Sambu Nagak and to Margaret Symington, which is the monodromy comes from the fact that the regular points are not simply connected, right? Because the monodromy, essentially, you take like a non-trivial loop, and then you say, oh, what happened to the torus as I went around that loop? But if the regular points were simply connected, there'd be no chance of monodromy. We'd be in kind of a nice situation. So what I'll do is I'll just take some line, some ray coming out of the focus point, and throw those points away, forget about those for now, and then say, oh, okay, away from that line, I can straighten out the affine structure. I can turn it into a polygon where I can now see all the invariants and learn everything I need to learn from this polygon. So the fact that it straightens out in just this nice way, I mean, it's a non-trivial statement, but I'm saying it like it's very easy, but it's not easy. Something else I want to point out is that because I have this global S1 action, there's like a preferred direction, which is like this vertical line, which is why I cut up in this case, so that the polygon, otherwise there's like a wedge missing or something like, otherwise it looks a little bit strange. But I could also have cut down, which is also like along my preferred direction, and it gives you a different polygon. And the thing about these two polygons is that on the left, they're equal, and on the right, they're related by exactly the monodromy matrix. So it's sort of just changing, it's like a change in branch cut. It's like defining complex log or something. So the point is that from the integrable system, you get some family of polygons that has to do with cut directions and things like this. And these polygons hold a lot of information, not all the information about the original semi-toric system, but certainly a lot of information. You can do a lot with just them. And so what I'm calling a marked semi-toric polygon is exactly what I've drawn here. It's a semi-toric polygon with a marked point for each focus point. And that marked point is at some height. And this encodes, of the 5 invariants that I very, very briefly mentioned earlier, this encodes 3 of them, essentially. I will essentially skip the fact that there are 2 more invariants that have to do with the dynamics near a focus point, but I don't know, I'm just gonna skip them. So there's 2 more invariants that have to do with what's going on at the point. But let's look at our example. I think I'm talking too slowly. So this is essentially the example I had before. I have a product of spheres. And now I have the same J as before. There's these parameters R1 and R2, which aren't too important. But I have a family of integrable H's. So it's a 1-parameter family of another function, which Poisson commutes with J. And if you start with t equals 0, J introduces a S1 action, and H also induces an S1 action. So you have a toric integrable system when t equals 0. So I don't know, I'll have to talk quickly, I have 2 minutes. So a point that will be important to me is north pole on the first sphere, south pole on the second sphere. Let me explain the system and draw a picture. So this is a well understood system that sort of is motivating what I'm going to do in the last 1 minute, which is that if you start with the parameter close to 0, you essentially have a toric integrable system. At some point, you have a degenerate system just for a moment, and then you get a semi-toric system, and then you have a degenerate system, and then you have a semi-toric system. This is easier to understand with pictures. And so it goes like this. You start with something toric, you deform it. Eventually, it's semi-toric. This point NS is in the interior. It's a focus point. It travels across, and eventually it's toric again. Essentially, it's almost toric, I guess. And the point is that for intermediate values of t, you have a semi-toric system. And I could, for those intermediate values of t, do the stuff that I just said, straighten out the affine structure and get 2 polygons. And it turns out that the polygons you get look an awful lot like the t equals 0 and t equals 1 moment images. And so it's supposed to make you think of this relationship between the affine structure and the actual systems that I built it out of. I perturbed it between 2 different systems, and it went some bifurcations. And so what I want to do is I don't know, I'm quite behind, I guess, but I'll say very quickly, what I want to do is start with a polygon that I'm interested in and use that to build the t equals 0 and t equals 1 systems, and then interpolate between them to build a semi-toric system that has the polygons I want. The t equals 0 system is toric, and therefore you can use Delzant's construction. So I'll give a highlight. So for instance, you can do something like that for polygons like this, which I'll say very quickly. See, we've done it. And a much more interesting polygon, I think, is the one with 2 focus points, because now, because you have more choices of cut directions, you have more sort of limiting systems to think about, which I'll finish with this, I guess. And essentially what you do is you come up with a toric system for each of these, and then you have to kind of carefully interpolate between them, and you can get a 2-parameter family of systems, that do, let's go up, that have one of the points become focus, or the other point become focus, or both points become focus if you kind of continue. And there's many more examples that I was going to click through, but maybe I should stop. I'm already over. So, thank you.
Some questions?
Yeah.
Along the axes, all
Oh.
along the thing at the far end on both axes, what is it? Almost toric or toric?
Yeah.
Toric?
So like the ones here, it's semi-toric with no focus points. So if I wanted to, for a system like this, I can do the thing that I said was illegal earlier, which is I can compose this with a diffeomorphism of R2 and get a toric system. So it is not toric, but not for any interesting reason, as opposed to these where you're really trapped. Yeah. So it's toric type is what it's called sometimes. So there's too much terminology here. Yeah.
Is it somehow very obvious how this interpolation works? Like, is it, so do you have to guess how the interpolating functions work, or do you have a
So
system
for the
that?
first 2 years, I was guessing, I guess.
Okay,
But I mean, the point is that there's like sort of different forces at play. Like, you know, the local normal form for a focus point has something to do with the eigenvalues of a matrix. And so eventually we were able to prove like a general theorem with Johann Laflaque. We have a very good understanding of how this will always work. I mean, I guess the easiest thing to say is that if you start with the toric system, then Delzant's theorem gives you that toric system as reduction on, in this case, it would be C4, which gives you actually preferred coordinates on this. You take the coordinates of C4, you know, upstairs. And the point is that when you want to move a certain focus point to the interior, then there is a preferred way to do it using those coordinates, which was not, like, for instance, this diagram is from my paper with Sonja Holach, where we were guessing in those days, but we now have a general framework. Yeah, it's a good question.
thank you.
Okay, so let's keep the question, further question to the break and thank the speaker again.